JAX on NVIDIA GPUs is already fast, but sooner or later you'll hit a wall. Maybe you need a fused OP XLA won't generate, maybe you need a custom memory layout, or maybe you're building something totally non-standard and you just need your own kernel. In this video, I'll show you a practical workflow for writing high-performance GPU kernels in Python using the CUTLASS CuTe DSL and then calling those kernels from JAX like their native JAX OPs. We'll go from here as a kernel to it runs inside JAX JIT, and then we'll go one step further. We'll introduce ahead of time compilation using JAX export so you can serialize an artifact and reuse it without ray tracing in the same Python process. If you've ever asked, how do I extend JAX with my own GPU kernels without leaving the JAX ecosystem, this is for you. So here's the plan. First, I'll give you the mental model, what CuTe is doing and how it maps to threads, blocks, and layouts. Then we'll walk through a series of kernels, starting simple and getting more interesting. Vector add, end-to-end, from kernel to JAX call. SAXPY, to show how to pass scalar parameters cleanly. ReLU, and then a fuse bias ReLU to show why fusion matters. A tiled GEMM example to show launch configuration and the limits of a simple implementation. Multi-GPU, how CUTLASS call still composes with JAX sharding. And then finally, ahead of time compilation with JAX export. Serialize, deserialize, and run the same compiled computation later. Plus symbolic shapes. I'll share the code and I'll call out the gotchas developers run into when they try this code for the first time. CUTLASS is NVIDIA's open source CUDA template library for building high-performance GPU kernels, especially things like GEMM and tensor operations. It gives you optimized building blocks instead of writing everything from scratch. Inside CUTLASS, CuTe is the tensor and layout system. It lets you describe a tensor as data plus layout, which makes tiling, indexing, and memory mapping much easier to reason about. The CuTe DSL brings those abstractions into Python. So instead of writing complex C++ templates, you can write GPU kernels in Python while still targeting the same high-performance CUTLASS infrastructure underneath. My colleague Michael gave a talk where he discussed the motivation behind all these tools. I'm linking it here, make sure to check it out. So in this video, we are combining CUTLASS performance primitives, CuTe tensor abstractions, and JAX composability. CuTe is best thought of as an index and layout DSL. On GPUs, performance often comes down to how threads map to data, how data is laid out in memory, and how you move data through registers and shared memory. CuTe gives you a vocabulary for tensor equals pointer plus layout. Instead of manually computing offsets, you express indexing in terms of tensor coordinates, and the layout handles the address mask. And the big practical takeaway is CuTe kernels are still CUDA kernels. Threads and blocks are real. You'll read the thread index, block index, and control launch shapes explicitly. CuTe DSL kernels come in two layers. The layer 1, CuTe kernel, defines the per thread program, the instructions each thread executes. CuJIT defines the launcher, grid, block, and the CUDA stream to run on. That second point is critical for JAX integration. The launcher takes a CUDA stream as its first argument, and that stream is managed by XLA. So your kernel runs on the same execution timeline as the rest of your JAX program. Let's start with the smallest complete example, vector add, C equals A plus B. In the kernel, each thread loads one element of A and one element of B into registers, adds them, and stores the result. Here are a few things to notice. We use thread index and a block index to identify the thread and the block. We use register fragments to keep the math in registers. And we use CuTe copy helpers to move data between global memory and registers efficiently. Then in the launcher, we pick a number of threads per block and a number of blocks in the grid, So the mapping between threads and data is clean and predictable. Now the key part, calling this from JAX. The trick is we wrap the launcher with CUTLASS JAX CUTLASS call that gives us a callable that can execute as a JAX custom call inside JAX JIT. Two important details. We must tell JAX the output shape and D-type upfront, so XLA can compile the graph. And for this kernel's indexing style, we reshape the 1D vector to a 3D view, elements per thread, threads per block, and num-blocks. That reshape is a layout reinterpretation, no data copy. We pad to a multiple of block size, reshape, call the kernel, and then reshape back and slice off the padding. I want to pause for a second and name the core pattern you will reuse. CUTLASS call bridges worlds. On one side, a Qt launcher that wants a CUDA stream plus tensors. On the other side, a JAX function that wants to compose inside XLA. So CUTLASS call turns the JAX launcher into a JAX primitive or custom call. That means you can put it inside a larger JAX JIT function. You can combine it with other JAX OPs, and XLA will schedule it as a part of the compiled program. The two recurring responsibilities you take on are: first, make sure your kernel's expected tensor layout matches how you present data from JAX. And the second, provide correct output shape and D-type so compilation is well defined. Once you get those right, everything else becomes repeatable. Next, SAXPY. Out equals alpha times x plus y. This is the same shape story as vector add, pad reshape to the 3D view, call the kernel, and reshape back. What's new is the scalar alpha. In the Qt kernel, alpha is just a parameter. But in JAX compilation, the question is alpha dynamic or is it static at compile time? For this demo, we treat alpha as a static argument. That means it's known at trace time and can be baked into the compiled code path. Practically, we do that by marking alpha as static in JAX JIT and then passing it into CUTLASS call as a keyword argument. This is a simple pattern, but it matters a lot. It lets you write kernels that take configuration parameters or constants without paying a dynamic dispatch cost. Now let's switch to a pattern you'll use constantly in machine learning: element-wise activations. For ReLU, instead of the 3D elements per thread layout, we use a flat 1D indexing approach. Compute a global linear index from block and thread indexes, bounce check, load, apply max from 0 and x, and then store. This looks a lot like standard CUDA kernel style, and the JAX wrapper becomes even simpler. Flatten the input, call the kernel with n, reshape back. This gives you a good feel for how Qt supports both styles. More structured, layout-centric kernels and straightforward CUDA-like indexing kernels. Here's where things get interesting: fused bias plus ReLU. In deep learning, X plus bias and then ReLU are common. But if you do them separately, you typically pay for 2 kernel launches and an intermediate write to global memory. Then a read back. Fusion avoids that. In one kernel, you load X, load bias for the column, add, apply ReLU, and store once. So the message here isn't Qt as a replacement for every JAX OP. The message is when you have a hotspot that is memory traffic dominated or launch overhead dominated, Fusion is a huge lever. In the wrapper, notice we also pass width as a static parameter because width affects indexing. And it's often helpful to treat it like a compile time constant. Let's do one advanced example, a tile GEMM. The point of this section isn't to beat CUTLASS code in JAX under the hood in JNP matmul. In fact, this simple educational GEMM won. CUTLASS is extremely optimized. The point here is to show the mechanics. How you decide the sizes, how blocks map to output tiles, and how you pass problem sizes like M, N, and K into the launcher from JAX. In the wrapper, we flatten A and B, provide M and K, call the kernel, and reshape back to M and N. One of the biggest questions developers have is, if I add custom kernels, do I lose JAX composability, especially multi-GPU? In this demo, the answer is no. A CUTLASS called kernel can still participate in JAX sharding. The mental model is as follows. JAX shards your arrays across devices. Each device runs the same custom call on its local shard, and JAX handles coordination. So we create a device mesh, define sharding specs, and use shard map to run vector add across multiple GPUs without changing the kernel code itself. That's a key selling point of doing this through JAX integration rather than launching CUDA kernels out of band. Now let's talk AOT, ahead of time compilation. Normally with JAX, you write a JAX-JIT function and the compilation happens in your current Python process. That's great for research and iteration, but in production, you often want a different workflow. Compile once, serialize an artifact, ship it or cache it, and load it later without retracing. That's where JAX Expert comes in. In this demo, we build a function that combines a CUTLASS custom call, an element-wise add kernel, and a normal JAX OP, like sigmoid. Then we export it, serialize it to bytes, and deserialize it back into a callable artifact. There are two key details when exporting CUTLASS kernel. First one, the exported computation includes custom calls. We explicitly tell JAX that these custom calls are safe to include in the exported output. Second, shapes matter. If we export with concrete shapes, the artifact is locked to those dimensions. If we export with symbolic shapes, we can reuse the same artifact across multiple input sizes within the constraints of the kernel's launch assumptions. So the headline: you can build a JAX program that contains a CuTe kernel, export it as a standalone serialized artifact, reload it, and run it later without needing the original Python function definition in the memory. Let me close the technical portion with a few practical tips that will save you time. First, always be explicit about shape and D-type for outputs when building custom calls. Second, decide early whether a parameter should be dynamic or static. Scalars like alpha or configuration values like width are often best treated as static. Third, pay attention to padding and launch constraints. If your kernel assumes full blocks, pad your inputs and slice the output. And finally, use this approach where it shines. Fusion, special layouts, custom data movement, and kernels that standard libraries won't give you. If you're trying to beat CUTLASS and GEMM, you're probably solving the wrong problem. If you want to go deeper on the conceptual side, I'll link the DevLab talk I've referenced earlier, and I also link the demo notebook and the kernel source so you can run this end to end. If this is useful, like the video, subscribe to NVIDIA Developer, and drop a comment with the kernel you wish you could write in JAX. I'd love to see what people are trying to build.